In these first couple of videos to introduce rotation, we're going to introduce angular variables. We need to talk about what angular quantities we're going to measure, how we're going to define our angular quantities, and we're also going to see what linear quantities that we've talked about previously these angular quantities relate to. We're going to see that a lot of equations that we've talked about previously are going to come up again with rotation, just with different variables in them. And so the first thing that we want to talk about is position of an object. Position for linear motion is where something is located along a line. The position x is where you are relative to an origin. And we talk about displacement, delta x, that's x2 minus x1. It's the change in position. For rotation, we have the same thing. But instead of talking about the position along a line, we talk about the angular position. We pick some angle where theta equals 0. Typically, that's the positive x-axis. And then we talk about the angle theta that something has rotated from that angular position of 0. The angular position is either measured in degrees or radians. If you're measuring it with a protractor, often you'll measure things in degrees, but typically we want to measure things in radians for rotational motion. And the reason we want to do that is because we often want to relate the angle that something has turned through with the linear distance that something has moved along the edge of a circle. The relationship between those two is the arc length equation that you learn in math class, that arc length S equals r times theta. But theta must be measured in radians. This is where the circumference equation comes from. The full distance around a circle, the circumference, equals r times 2 pi radians. Again, that's the relationship between degrees and radians. If you forget it, there's 2 pi radians in a full circle. There's 360 degrees in a full circle. Just like with linear motion, we often care about the change in position. The same thing is true with rotational motion. We often are interested in the angular displacement. The angular displacement is the later angular position, theta 2, minus the earlier angular position, theta 1. And so right away we can see that there are similarities between the linear quantities. Delta x equals x2 minus x1 for displacement, and delta theta equals theta 2 minus theta 1, the change in angular position, for angular displacement. Linear displacement is change in position. Angular displacement is change in angular position. The rate of change of the angle is the angular velocity. How quickly the angle is changing is the angular velocity. So again, rate of change is how quickly something is changing. So the rate of change of the angle is the angular velocity. If we remember what we had with linear motion, average velocity was defined as displacement divided by time, delta x over delta t. Instantaneous velocity was the derivative of x with respect to time. For angular motion, we have that average angular velocity is the angular displacement divided by the time. Again, same equation, just with angular variables. So the average angular velocity equals delta theta over delta t. And the instantaneous angular velocity is the limit as delta t goes to 0 of delta theta over delta t. That's the definition of a derivative. So the instantaneous angular velocity is the derivative of theta with respect to time. The symbol that we have for this angular velocity is this Greek letter omega. It's a lowercase omega. And the units for angular velocity are radians per second, because our angular displacement is measured in radians. But radians technically are a unitless quantity. It's a dimensionless quantity. And so sometimes you'll see radians per second written as just 1 over seconds, or sometimes you'll see it written as seconds to the negative 1, which means 1 over seconds. The name that's given to 1 over seconds is also hertz. So sometimes you'll see angular velocities written in hertz. I tend to prefer to leave it in radians per second. It reminds you that you have an angle changing with time. And we refer to these new equations as equations that are analogous, similar to equations for linear motion. These are our analogous equations for rotation. Average velocity was displacement divided by time. Average angular velocity was angular displacement divided by time. Linear instantaneous velocity was the derivative of the position x with respect to time. Instantaneous angular velocity is the derivative of the angular position, theta, with respect to time. So you see that while these are new equations, they're actually very similar ideas to things that we have looked at previously. So if we have something moving around the edge of a circle, we sometimes will talk about the tangential velocity, its tangential speed. And that is how quickly its position is changing. Again, that speed was dx dt. When we talked about uniform circular motion, it was that tangential speed that was staying constant as something moved around in a circle. We're going to see that there's a relationship between the tangential speed and the angular speed. If you are looking at a particle that's moving around the circle, then you're looking at a line drawn to that particle and to talk about its angular position. And so we're talking about how quickly that angular position is changing. That's what omega is. But that distance along the edge of the circle, the arc length, is related to the angle. So we're going to see that the tangential velocity is going to be related to the angular velocity. The arc length equation says that S equals r times theta. If I take the derivative of S with respect to time, that gives me the tangential speed. It gives me how quickly it's moving along the edge. If I take the derivative of the left-hand side of the equal sign with respect to time, I have to take the derivative of the right-hand side of the equal sign with respect to time. So the derivative of r theta with respect to time, where r is constant, is r times d theta dt. But d theta dt is omega. So we have this relationship that the tangential velocity is r times the angular velocity. And these are important relationships. If you have a ladybug that's sitting on the edge of a turntable and that turntable is going around, they might talk about the angular speed of the turntable. But that ladybug going around in a circle has a certain tangential speed as it's going around. And so that tangential speed will be r times the angular speed. The farther away it is from the center, the bigger that tangential speed is, even though the angular speed is the same. When we talked about circular motion, we talked about frequency and period. Frequency is how often something happens per second, how many cycles you have per second, how many times going around the circle you have per second. So frequency is revolutions per second, or trips around the circle per second. Period is how much time it takes for one cycle. There's one cycle per period. The period is seconds per revolution. So frequency is the inverse of the period. Angular velocity is radians per second. One revolution is 2 pi radians. In one period, the object turns through 2 pi radians, one revolution. If something has an angular velocity of 1 revolution per second, that would be 2 pi radians per second. So we can convert from revolutions to radians. Sometimes you're asked, how many revolutions does something turn through? Sometimes you're asked, how many radians does something turn through? There's a relationship between those. It's similar to converting from meters to centimeters or meters to kilometers. It's just a different way of describing that angular distance. Angular velocity, omega, is in one turn, it turns 2 pi radians, and the time that it takes is the period. So angular velocity is 2 pi radians divided by the period. But since period is 1 over the frequency, that could also be written as that the angular velocity, omega, is 2 pi times the frequency. This angular velocity equation is equivalent to what we had with uniform circular motion. We said that the speed in uniform circular motion was the distance 2 pi r over the period. Well, here the angular velocity is the angular distance that it travels. It's 2 pi radians divided by the period. So far, we've talked about angular position and angular velocity. In the next video, we're going to look at angular acceleration and relate it to linear acceleration. And then, After that, we're going to look at our rotational kinematic equations, our equations that relate the angular position, angular velocity, and angular acceleration all together, specifically for things where the angular acceleration is constant. We're going to have constant angular acceleration equations, just like we had constant acceleration equations for linear motion.